All right, so we finished yesterday talking about aromatic systems. We said that the old definition was just based on smell. The modern definition uses this 4n plus 2 rule that we're going to cover today. And then we went over basic nomenclature. We said that with dye-substituted rings, there's oftentimes this use of ortho, meta, or para to describe the location of your two substituents. And then we said that these older names have held on even through all the IUPAC nomenclature rules. And these are generally used as parent names. And we went through and we did a couple examples with TNT, metachlorobenzaldehyde, and then metachloroperoxybenzoic acid. But now let's kind of take a step back and ask, why are aromatic rings so special?
The original structure?
Yeah, we're going to look at a few different things. There's a couple of different things going on with aromatic systems. And in order to make this point, I'm going to compare two different reactions. Let's say I want to go from cyclohexene to cyclohexane. What reagents do I need?
H2
Yep, hydrogen gas and some sort of catalyst like palladium, platinum, sometimes even nickel. And you can do this experimentally in a calorimeter and measure how much heat is evolved in this reaction, right? So in this reaction, it is exothermic, and the heat is negative 120 kilojoules per mole, right? So it's an exothermic reaction. If we try to do the same thing with benzene, we actually have to use very, very special equipment. Typically, we still use hydrogen, but we have to use a high pressure system and nickel catalyst. So I'm going to write high PSI, indicating high pressure. And what should the enthalpy be based off of our observation with cyclohexene?
3 times.
Yeah. So we'd say we would expect delta H not to be negative 360 kilojoules per mole, right? However, the interesting observation is that this isn't what you get. The actual enthalpy is negative 208 kilojoules per mole. So it actually doesn't release as much energy as you would expect when you're reducing every single double bond in a benzene. In fact, if you do the math, you could say that there is 152 kilojoules per mole of aromatic stabilization. And this is in comparison to a normal alkene system like cyclohexene. And this explains why the benzene ring, the double bonds within it, don't do the normal reaction that double bonds do, right? So if we remember back to last, or I guess not last term, this term, we had alkenes do all sorts of addition chemistry. So we could take something like cyclohexene. We could react this with bromine. And what sort of product will we get? Will it be syn or anti? Anti. However, if you take benzene and you react it with Br2, you get no reaction. The double bonds in benzene don't behave like normal double bonds in an alkene system. Why is this? Does anybody have an idea?
Resonance structure?
Yeah, when in doubt, the answer is resonance, right? It's a safe bet. Let's take a look at the orbital picture. We know that the double bonds in benzene aren't true double bonds, that the resonance structure actually has those double bonds delocalized through the whole ring, so they're more like bonds and a half. So let's draw the resonance structures. And we know that the bond order is 1.5, meaning our carbon-carbon bonds aren't true single bonds, aren't double bonds. Oftentimes, people will draw this using the hybrid view, kind of like we saw during first term, and they'll draw this using dashed lines to indicate that those pi electrons are actually delocalized around the ring. And oftentimes, to avoid drawing dashes, chemists will just draw this as a circle. You can draw it either way. It's fine to draw it as a circle. I'll understand that you mean it's a benzene ring.
Can you explain what is a bond order?
So a bond order of 1 means a single bond. Bond order of 2 means a double bond. Bond order of 1.5 means it's in between a single and a double bond. Yep. Okay. So let's take a look at what's going on at the molecular orbital level. And in order to do this, I'm going to draw out all of our carbons. And I'm going to do my best artistic rendering of a side-on view. Oh. Okay. What's the hybridization for all of the carbons in benzene? sp2. So I'm not going to draw the hydrogens, but we know that we've got these p orbitals. And in fact, I'm going to draw them using different colors. So we've got a p orbital with these red and blue lobes, meaning that they're not the same phase. You've got some that are opposite phase. And the electrons in this pi system will actually delocalize across all of the adjacent p orbitals. So the electrons will delocalize across all the aligned p orbitals. Make sense? All right, now we get to go into more complicated systems. Is it okay if I change page? No? All right, I'll give you guys a second. That was pretty unanimous. I know, it's like you guys are copying the Mona Lisa right now, but yep. Yeah, so remember that your p orbital has equal probability of being on either face. So the pi cloud is both above and below the benzene ring in terms of the molecular orbital picture. I'm not going to draw the red cloud just because it'll make... I guess I could. You've got pi delocalization across both faces. Yep. Yeah, what I'm trying to do is a side-on view of benzene rather than a top-down view, and so I'm trying to draw it with a little bit of perspective. All right, now we're going to learn a new rule for aromaticity. This is called Huckel's rule or Huckel's rule. Unfortunately, Mike's not here to correct my German pronunciation. But he came up with this idea that molecules exhibit this stabilization when they have 4n plus 2 pi electrons. So molecules are aromatic if they have 4n plus 2 electrons located in p orbitals that are aligned in a ring system. So just like we saw with benzene, if we take a look at benzene, we could ask ourselves, all right, how many electrons are in those p orbitals? we could say, well, there's 2 electrons accounted for here. There's 2 electrons here. And there's 2 electrons here. So how many total electrons? Well, just 6, right? So we've got a net of 6 electrons, which means if we try to do our 4n plus 2 rule, we would say, all right, 4 times 1 plus 2 equals 6. The question is, well, what does the n stand for? N is an integer. Right? So n can be 0, it could be 1, it could be 2, it could be 3. As long as your net output, meaning this value over here, follows this rule, the system can be considered aromatic, right? So let's take a look at some example systems that aren't benzene. And I want you guys to help me determine if these are aromatic or not. We'll throw benzene on there for good measure. First thing I always do is I try to count all of the electrons in that system, including the electrons that can be in a p orbital, whether that's already in a pi bond or a lone pair. You guys have these all written down? All right, let's take a look at the one on the far left. How many electrons are in p orbitals? 4. Does this follow the 4n plus 2 rule? No, there is no integer n that would fit that and give you an output of 4, right? So if we look at this, this is actually something called anti-aromatic, meaning it follows the 4n rule, not 4n plus 2. Let's take a look at the next one. How many electrons are in the next one?
5.
Well, remember, we've got this lone pair here. Is that lone pair going to be in a p orbital or an sp2 orbital or in an sp3 orbital? What do you guys think? It's going to be in a p orbital, right? You can delocalize that lone pair all the way around the ring, which means it's got to be in a p orbital, right? So we count those 2 electrons in that lone pair, and then we've got 4 electrons in our pi system already, which means we've got a net of 6 electrons. Is this aromatic?
Yes.
Yeah. So we can circle this and we can say this is aromatic. What about the next one?
No.
No. If we look at the next one, we don't have that lone pair anymore. There's a carbocation at the top. This is 4 electrons in the ring system. So if we count all of the electrons, it doesn't work with the 4n plus 2 rule. Instead, again, this is anti-aromatic.
Wait, wouldn't this be 2?
For which one?
The one you just did.
So we've got 2 electrons in each of the double bonds that I've shown. So that, but positive charge doesn't have any electrons. That's the absence of electrons. Yeah, so we only can count the pi electrons in this case, not the lone pairs because they're not there. All right, benzene we said has 6 electrons, so this would be aromatic. And then what about the last one? 8 electrons. All right. In systems like the one shown on the far right, in fact, they're so unhappy with 8 electrons, what they end up doing is kind of contorting a little bit. I'll do my best to draw this in 3 dimensions. And let's imagine we're doing a side-on view of this molecule. So this is our front side.
Why you chose both conformation instead of chair conformation?
Because this is an 8-membered ring, right?
So
we've got a double bond here.
The chair now?
For 8-membered rings, instead of adopting a boat, you actually adopt a tub conformation. They're tub-shaped. So anti-aromatic compounds are inherently unstable, and oftentimes, to avoid being anti-aromatic, they'll actually adopt different geometries that will force them out of planarity. So now if we look at the p orbitals in that last example, they're no longer aligned and they can't delocalize. That makes this molecule more stable. So this would just be non-aromatic. Nope, because anti-aromatic systems, you still have to have aligned p orbitals, right? They have to be able to crosstalk to one another. And in the other examples, we're forcing them into planarity. This one can actually twist out of planarity. Yeah. Yep.
So, is there an easy way to differentiate between something that's anti-aromatic and something that's just non-aromatic?
On exams, without knowing whether or not it's planar or not, I'll give you some sort of hint. I'll say these are all planar systems, or assume that they're all planar systems, or something like that. Unless you know a little bit more about the system, it can be tough to tell. There is one trick I want to show you guys, though. What about this system? Cyclopentadiene, that was the one we saw for all of our Diels-Alder reactions. Is this aromatic?
No.
No, this is not aromatic.
So it's anti or just non?
Well, let's think about this. How many electrons are there in the ring system?
4.
4. So our gut instinct would be to say this is anti-aromatic. However, if we look at this position, there's no p orbital, right? This carbon's actually sp3 hybridized. Anytime you see an sp3 atom in a ring system, it can't be aromatic or anti-aromatic. It's just not aromatic. It doesn't fall in any category. So sp3. Anytime there is an sp3 carbon or atom in your ring system, it is non-aromatic. Does that make sense? You can't delocalize through an sp3 lobe. Make sense? All right. Now we get into more complicated systems. Aromatic heterocycles. Yep.
You mean not?
Yeah, not or non-aromatic. It doesn't fall into a category of aromaticity or anti-aromaticity. It's just none of the above sort of thing. All right, let's take a look at some aromatic heterocycles. I've got a couple of examples. A heterocycle just means it has a non-carbon atom in the ring system. Does anybody remember the name of this compound? Pyridine. When do we use pyridine? Yeah, tosylation. It's a really good non-nucleophilic base. I've got another one that also is a heterocycle that contains nitrogen. This is called a Parole. And now we have to look at these and we have to determine whether or not pyridine and Parole are aromatic. First thing we typically do is we have to analyze the orbitals and make sure we've got p orbitals and then count how many electrons are in the p orbital system in the ring. So let's take a look at pyridine, and I'm going to do a side view of pyridine, kind of like we did with benzene. So I'm going to have nitrogen coming off of the end. And then we've got this lone pair kind of sticking out to the side, right? Each of these carbons has a p orbital, right? Because they're all involved in a pi bond. And then the nitrogen also has a p orbital because it's involved in a pi bond, right? So we've got one pi bond right here. We've got another pi bond right here, and we've got another pi bond right here. We've got 3 pi bonds in this ring system. So I'll label this as pi, pi, pi. Right, so if we go through and we try to count how many electrons are in the p orbital system, how many would there be? 6. Is this aromatic? Yes, it's going to be aromatic. Why don't we count the lone pair?
Outside the ring.
Yeah, it's outside the ring. It's not in an aligned p orbital in that pi cloud, so we don't count it. In fact, what orbital is the lone pair in? Would it be sp, sp2, sp3? sp2, right? If we look at that nitrogen, it has 3 different groups around it, so it's going to be sp2 hybridized. That means that this lone pair is actually going to be sticking out into an sp2 lobe. Lone pair not counted. All right, let's do the same thing with Parole now. Yep.
Why did you count the one with the negative charge as aromatic?
That's a good question. So if you look at that negative charge, it can be located, that lone pair, in a p orbital, and the hydrogen could be in the sp2. So let's take a look at Parole, and then we'll come back to that. All right, so with Parole, again, I'm going to try my best to do this side-on view. We've got this p orbital here, here, here. Oh shoot, I gave it away. All right, if we look at this, the question is, will the hydrogen be here, or will it bond off the edge right here? It'll be sticking out, right? Vespers theory indicates that the atoms want to be as far apart from each other as possible. So the hydrogen is going to be located out in this position for Parole. It's going to be planar, which means that our lone pair electrons are going to be located in this p orbital sticking straight up and down, right? Because the hydrogen over here is occupying the sp2 lobe. So if we look at this, we could say, all right, there's a pi bond back here. That's 2 electrons. A pi bond right here, that's 2 electrons. And then we've got the 2 electrons in that p orbital coming off of nitrogen. So again, we've got 6 total electrons in our p orbital system. So if we think back, going to our previous example where we had that negative charge, we'll do one last one. We've got this negative charge up here. That means if we were to draw this out, we'd have carbon, 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 carbon. Oops, let me clean this up. So we've got one pi bond here. We've got one pi bond here. We've got hydrogens coming off of all of these carbons. Let me even draw them coming off here. Okay, I'm going to move these over. We know that this hydrogen, due to Vespers theory, is going to be sticking out away from the ring. But that lone pair on the carbon, this lone pair, is got to be in this p orbital. So again, in this system, we have 6 pi electrons, right? That's what makes this ion aromatic. It doesn't need to be a neutral molecule to be considered aromatic. All right, now I've got a good challenge for you guys. All right, this is another heterocycle. This is called furan, and it's got double bonds here and here. Is this aromatic? It's kind of a tricky question. I've heard students say there's 2 lone pairs, so we've got 4 electrons that are lone pairs. We've got 4 electrons in the pi system, so wouldn't that be 8 total electrons and violate Huckel's rule?
Does the one row electron pair be in P-orbital and
Yeah, that's a good question. Can you have 2 lone pairs in a p orbital coming off of the same atom? No. So let's draw this using our molecular orbital picture. Sorry, this should be an oxygen. So we've got a p orbital here and here. Oh, that's a bad p orbital. So in furan, we've got 2 pi bonds, right? Pi here and pi here. And then this oxygen over here is actually sp2 hybridized. Why isn't it sp3 hybridized? Oh, this gets back to first term stuff, right? So let's consider resonance structures. Right? Anytime a lone pair can delocalize, it will delocalize. So in this case, we can move a negative charge over there, have oxygen with a positive charge. And in this case, you can tell it must be sp2 because over here, it's sp2. So there's quite a few other resonance structures for this, but remember that anytime you have a lone pair that can do resonance delocalization, you have to reconsider its hybridization. So in this case, oxygen is sp2. Which means one set of electrons is located in a p orbital. The other set of electrons is going to be located in the sp2 orbital.
Being aromatic, you have to have 6 electrons.
Yes, you have to have 6 electrons in your p orbital system, right? We don't look at sp2 lobes, we don't look at sp3 lobes, we only look at p lobes. So in this case, how many electrons do we have in our p orbital system? Yeah, 6 total electrons in p orbitals. That means that this is aromatic. All right, another kind of tricky one. Let's consider this system. Is this aromatic? Does anybody have a hypothesis they want to throw out? What was that, Sarah?
I'm not confident enough to.
Be bold, be brave. It's conjugated, but is it aromatic? Yeah, but remember, the p orbitals have to be in the same ring system, right? So if we look at this, this is an exocyclic double bond, meaning it's sticking out of the ring system. It's not a part of the ring system. Are not counted. So in this case, this wouldn't quite be an aromatic system. Instead, these would be localized pi bonds, right? It's a little bit confusing, but just remember, you want to count 4n plus 2 electrons in p orbitals in the same ring system, right?
So would that be anti-aromatic?
No, in this case, it would just be localized pi bonds. With anti-aromatic systems, it gets into more advanced chemistry, but in this case, this would behave more like just a diene.
Okay.
Yeah. Yep.
What about its resonance structure? I mean, because that's like, it looks like it could have a resonance structure in the ring, right?
That's a good question. So the question you could say is, well, why can't we take this pi electron down and have this be positive, this be negative, and then you could say, well, now we've got 6 electrons in our ring system. But what did I say about resonance structures where you have carbons next to another carbon where you've got a positive and negative?
This is not favorable.
Practically doesn't exist, so don't worry about that. That's such an unfavorable resonance structure. You might as well not even consider it. Yeah. All right, let's do another one. Since you guys like these.
Professor, but if you had like a ketone on the top, like an oxygen, then would you have some aromatic like interactions?
You saying an oxygen right here?
Yeah.
No, because you would still have a p orbital on that oxygen, but it wouldn't be contributing to the pi system in the ring. You have to look at the overall pi system. Yeah, it's a little bit confusing. Let's do another one. I just thought of this one, though. Oh man, I hate these rings.
Maybe you can take some art class.
Yeah, maybe I should take art classes. What about this ring system?
I don't know what to believe anymore.
How many electrons are in the ring system of p orbitals, right? 6. So in this case, this would be aromatic. So only 6 electrons in the ring system. Therefore, this is aromatic. All right. Does anybody here suffer from allergies? Yeah. Here's a good one for allergy sufferers. This is histamine. I want you to determine if the ring in histamine is aromatic or not. Yep.
So I think the electrons on the nitrogen on the top would be included at the bottom of it.
Okay, so the electrons on the top would be included. Why?
Because it would be
Yeah, because they have to be in a p-orbital to delocalize. We could do resonance structures pushing those electrons around the ring. So these can delocalize.
And the hydrogen is in the sp2 orbital, right?
Yes, exactly. So the hydrogen's in the sp2 orbital. The lone pair must be in the p in order to delocalize. What about this lone pair? No, all of the p orbital is already occupied by that pi bond, so we can't have two sets of electrons in the same p orbital, so these are not counted. P is already occupied. So if we look at this, how many total electrons do we have? 6. Oop. Therefore, it's going to be aromatic. Right? Not too bad. You just have to go through the same sort of thought process anytime you're analyzing whether or not a molecule is aromatic. They don't do traditional pi bond chemistry that we saw in Chapter 9. All right, we do have to cover a couple of new reactions. However, most of it's pretty straightforward for this chapter. With the frost circles? If you want, you can go through and read your textbook on frost circles. However, I've found that occasionally students look at that and they're like, what is going on? He's drawing polygons and stuff. This works. So if this system works for you, great, you can stick with it. If you want, you can go back and read frost circles. I need to double check sapling to make sure I took out all the frost circle problems though. Yeah. There are. Okay, I'll go in and take out the frost circle one.
So we're not required to know how to do it.
You're not required to. This system is just as effective as the frost circle method. Yeah. All right, let's take a look at some of the reactions for Chapter 18. They're really not too bad. That usually means bad. No. All right, so if we look at this compound, where do you think the benzylic position is going to be? Yeah, first carbon coming off the benzene. This is referred to as the benzylic carbon. And it tends to be very reactive. Why is that?
It's primary? No.
Well, it's secondary. Yeah, it's a little bit of both. It's kind of allylic. It's kind of due to the pi cloud. The benzylic position is very stable due to the resonance occurring in the neighboring benzene ring. So just like we saw with allylic systems, they form really stable carbocations. Benzylic positions also form very, very stable carbocations. So oxidation chemistry occurs very readily here. So let's take a look at this compound. What's the alternate name for methylbenzene? Toluene. We can actually convert toluene directly into this compound. And what's this compound called? Benzoic acid. And in order to do this, we use a really strong oxidant. Because if you look at this carbon in the benzylic position versus this carbon here, this has an oxidation number of -3. This one has an oxidation number of +3. So we're transferring electrons in this reaction, right? Specifically, we're losing electrons, so this is oxidation. What's a really good oxidant we could throw at this to oxidize these carbons? Chromic acid. Na2Cr2O7, H2SO4, and water will oxidize that carbon all the way up to an oxidation state of +3 and give you benzoic acid. The other system that's occasionally used is you can also get to benzoic acid by using potassium permanganate. So that's KMnO4, water and heat, followed up by an acidic workup. Oops, forgot my double bonds in there. Either one of these methods can be used to form benzoic acid. All right, let's try another one. Let's say I throw in Na2Cr2O7, H2SO4, and H2O at this compound. So the chromic acid oxidation. No reaction? Why? Yeah, exactly. You guys remember back to oxidation chemistry with alcohols? We said that you can't oxidize a tertiary alcohol. You can't oxidize a quaternary carbon, right? You don't have any alpha protons. So in this case, there is no reaction. There are no alpha protons. One of the strange things is, well, what if we took this compound and treated it with the same reagents? Do we have alpha protons? Yeah. So now the question is, well, what will this turn into? Not quite. This will actually cleave off other alkyl spinach hanging off of your molecule and still give you benzoic acid. Oops. So when you oxidize these, essentially we will lose any non-benzylic carbons. So we lost that terminal ethyl group that's kind of dangling off there.
Can you show us an example of some reaction that doesn't lose anything?
Well, the top example where we had toluene, we didn't lose any carbons there because we only had a benzylic carbon that was being oxidized. But if you have a carbon that's coming off, meaning further away from that benzylic position, it will get cleaved off and won't be a part of your product molecule.
And if there were two carbons, we'd still be able to get a reaction, right?
Yeah, if it were an isopropyl group, for example. So you're saying, well, what if we had a carbon here?
Yeah.
Yeah, because you still have an alpha proton, you would cleave off both of those methyl groups.
What is that called?
This is just called oxidation.
No, the molecule.
Oh, that would just be ethyl benzene.
Okay.
So ethyl group coming off of the benzene. Yep. What's that? Oh, shoot. Thank you. I do this all the time, and it's one of those things where apparently I learned how to write it correctly, and my brain just won't accept it. It's like, no, you're going to look like an idiot while you post this on YouTube. All right. One last reaction is free radical bromination. All right, let's say we've got this compound, and we treat this with NBS and heat. Where do you think the bromine will get installed? Benzylic position. Why not the tertiary position? Yeah, the benzylic radical is actually more stable than a tertiary radical. So in this case, the benzylic position will be far more reactive than any of the other positions. So we'll brominate this carbon. And do we have to worry about enantiomers?
Not in this case.
Well, let's think about it.
Oh, yeah.
Have we formed a stereocenter? Yes. So in this case, we'll get a racemic mixture of our free radical bromination product. I think we're going to stop there today. Tomorrow when we come back, we'll go through the free radical mechanism again, and then we'll learn one last reaction and then do some synthesis problems.